Let's talk about databases in cloud. Most of the application you are using would have some type of databases behind the scene. Databases is a good way to store data in a structured format so that if required, we could trace back that data, we could query that data and get the result and maybe satisfy business or technical requirement of my application. So let's see how we have different type of database options in the cloud, how we implement these solutions in cloud. But before we discuss about implementation details, we need to understand some of the basic difference in the way databases store data. And that brings us to discussion of talking about SQL versus NoSQL databases, or I would prefer to call them relational versus non-relational databases, right? What we are discussing here is a pattern how the data is being stored inside a database. Like if you look here, this looks like a tabular format of storing data, whereas this side here, it looks like a hierarchical format of storing the data. The data may be same, but the way we store could be little differently implemented. Now, I personally don't prefer to call them SQL versus NoSQL because now our non-relational databases have evolved so much that even they can understand SQL. So you could run a SQL query on a traditional relational database, or you could also run SQL query through some type of engine or some type of middle layer in between, so that your non-relational database will also split or will also spit the output into a SQL format. So that's why I prefer to use relational versus non-relational rather than calling it SQL or NoSQL. Let's try to understand the pattern of data by using an example. Let's take a recipe card here. This recipe card is for making a banana bread. On one single page, I am getting details about the ingredients required. I am getting details about the steps to follow and more information like how much time it takes, is it easy recipe, how much it would be sufficient for. So this is one single page in a recipe book in which all the detail to make banana bread is there. I don't have to keep on going to different pages into the recipe book. One page is good enough. If I keep on following and if I all ingredients, I would have the banana bread baked up for me, right? I haven't tried this, I've just taken the picture, but in case you try this, let me know how this bread tastes and maybe I can give it a go. Now, let's focus on these ingredients. Now, you may be thinking why I'm talking about banana bread and all. I would relate these concepts into a minute and I will explain you that how this is representing a type of database. So in this case, if I have to get these ingredients required for banana bread, obviously I have to go for grocery shopping. If I go to grocery store, what you will find that they have stored these items in different racks, and I may have to go to different racks and then what I am looking for. So maybe for banana, I would get it from here. Maybe I need drinks like milk and all, I would get from here. Maybe I need some crisp, may I need some cheese. So what I'm doing, I'm filling up my shopping cart by items which are coming from different racks. Think of these racks as your tables in which your data is stored. And you run a SQL query, which is your shopping cart. And to satisfy the query, what would happen? Probably that your data may be pulled from multiple tables, combined together and then delivered back to you. That's what is a traditional SQL database is. Here, the data is being stored into different tables, and when you run query, that time there would be some way by which your SQL engine running behind the scene will pull up data from all these locations, massage it as per the way you want or as per the query you requested, and then deliver that data to you so that you could process it further. So idea here is my data is spread, and obviously there may be some relationship between these tables, like probably these two things needs to be kept cool, so they would be kept nearby so that this will be maybe whole cooling fridge, right? Just giving an example, it could be anything, but there is some relationship between these things which are being stored inside these table. On the other hand, when I had my banana bread recipe, I did not had to go to different places. Just one page has all the information. This is a type of a non relational database which is into play. In one document, I am getting all the information I need, whereas in case of a traditional relational database, my data would be spread across multiple tables, and then I would be running query which will bring data from different places and deliver me the result if I am looking for what I am looking for, right? So differentiation between them. SQL databases are optimized for storage. What I mean by that, I'll explain that in a minute. NoSQL are optimized for performance. I'll explain that too. Now, data storage in terms of SQL database is rows and columns. All my data is stored into rows and columns, and I would have tables, and through these tables my data would be stored. So let's say this is my music table, and then there is a artist information here, maybe album information here, and that's how I would create relationship between these databases, and that's why they are called relational databases. These are all representing different tables, and by combining a table and then running query against it, I would get the result. Whereas if I'm talking about NoSQL database, maybe NoSQL database stores my data in a document format like a recipe card. And then everything is available here. If I'm looking for, let's say, year for Jane Doe, first and last name, I would just need to go to one document and I would get this information. Whereas in this traditional way of doing things, maybe the name is stored in this table, maybe the year is stored here, and maybe the ID is stored here, and there would be some relationship between these tables. So hope you are getting the idea. Now, let me explain what we mean here by SQL databases are optimized for storage and NoSQL databases are optimized for performance. Let's talk about it. Why this is. Let me show you a picture here. If you're guessing, this looks like very old picture by the way people have dressed and the way it looks, the black and white kind of a stuff, lot of manual work happening, and it has something to do with technology. As I can say, this is IBM Data Processing Division. What you are witnessing here, it is a 5 MB hard drive being shipped from IBM. 5 MB. Imagine that. So 5 MB hard drive is being shipped from IBM, and this was called a portable hard drive. Yes, it is portable with 8 men and 1 van. It is portable. Now, what we are trying to explain here that how storage has evolved. See this picture now. What you are seeing here on your fingertip, there is a 1 terabyte memory card. So in early days of computing, storage was very costly. Very huge cost was there for storage. So whatever systems were designed, they were designed in a way that they would optimize storage. Instead of keeping data in duplicate fashion, they would ensure that data is kept uniquely, and then we build relationship on top of that data to get that information. And that's what I meant when I said my SQL databases were optimized for storage. They were trying to minimize the space consumed for storing data, whereas by the next time, like this happened around 1970s, somebody in IBM invented these relational database, and there is nothing wrong with that. We still use a lot of relational databases, but as technology evolved, let's say when Web 2.0 came mainstream, applications like Facebook and then Google and Amazon, where millions of users are using the application, the traditional approach of SQL based databases was not scalable enough. And that time, what used to happen previously, as your data load keeps on growing into your database, the query will become slower and slower. And if I'm talking about an application which will be used by millions of users, and if data keeps on growing every day, my SQL query or whatever query I am writing would keep on becoming slower and slower. We didn't want that, and that's why this new breed of databases were created. Those are referred as NoSQL database, which are designed for performance, optimized for performance. So whether one user is accessing the data or one user's record is there or millions of users record is there, they can still give you the performance which will be optimized for your workload. So that is what we mean by a NoSQL database. If you look here, I have mentioned different type of storage techniques. In a SQL database, data is stored in tables and rows and columns, but in NoSQL, there are different ways to store data. One I have displayed here is a document format. This is a document, not your Word document, but typically a JSON document, and here we have data being stored into a key value format, and we may have a hierarchy like this is a top level unit, and within that we have first and last name, and this is another independent unit which we are storing inside. So that is a document way of storing the data. Another way of storing the data could be a key value pair, very common, right? So I want to store someone's name, so name it will be a key and the value will be whatever the name is. I want to store someone's age, and then age would be something here. So that is what we are referencing here as a key value pair. Now this is same data but put together into a different format. Then we also have another way of storing data, which is graph format. So graph format databases are good when you have a lot of relationship data to be maintained. Like when we have social media application, A is friend with B, B knows this person and C knows that group, or C likes that product. So when we need recommendation engine, when we need to do fraud detection, when we need to do social media networking, that time this this graph databases would be very helpful because they are storing the relations inside a database. Right. So question you may have, can I not deliver the same result from SQL? Yes, you can, but it is not optimized for it. The time and effort required to create this kind of a relationship structure and to create optimization will take more of time, and that's why these can be a very specific use cases which you want to fulfill by your key value pair, graph or document, and one more which is referred as wide column. So these wide column databases are very good way to store your analytical data. When you have a lot of analytics to be done, that time maybe you could utilize this wide column databases too. We will focus on some of these aspects as we move forward. So I hope this thing is clear that what is the difference between a relational and non-relational database. It is the way they store data. Right. Let's talk about a little bit more details on that. When it comes to schema, schema is the pattern how I am storing the data. So maybe we have created schema that we would have name here. Maybe we would have age of the person here, and maybe we would have, let's say, date of birth of that person. Just giving an example. So this schema somebody has thought initially, and that would be followed throughout the life cycle of the database. Schema design is an important aspect for SQL or relational databases because once you designed that and once you implemented it, it has become fixed, right? And let's say if you have a person's value to be stored, let's say name is XYZ, maybe you do not know their name, maybe you do not know their date of birth, so you can't keep them blank. Technically, what will happen that the system would fill itself with the null values here saying that, hey, this data is not there, so null value has to be added because it expects is to have the fixed schema, like you have a form to fulfill and in that first name and last name is required, that is a fixed schema. Now what if somebody has first name, middle name and last name? Now my upper section of the form is not designed for it. That is a fixed schema. Only I have first name and last name, but maybe sometime I may want to keep my schema dynamic. What if I come up with the situation that like for some people, they may have first name, they may have a middle name and they may have a last name. We want flexibility. So if you're looking for that flexibility that your schema can change, that time your NoSQL or non-relational databases are good. I am trying to depict it here. So some records which you see here or some items which we call them, we may have here things like this one has 2 attributes inside, this one has maybe 5 attributes, again 2 attributes, again 4 attributes. So that is completely okay with NoSQL databases. They expect schema to be dynamic and it can evolve over a period of time. There may still be some mandatory values, like let's say the first field is required and then second field, third field or fourth attribute or fifth attribute is not required. That can happen. That is what we mean by a dynamic schema. Right. When it comes to query these databases, SQL databases support just a SQL statement. Probably you have at least seen some SQL somewhere in your life. So see this thing here, very simple one. So we want to return all of the song by artist Elvis. So we say select star representing everything. From the table called music, where the value we are looking for, where the artist information is Elvis, and deliver me all the song by the artist Elvis. Now, I could write the similar type of query for NoSQL databases too, but the format would be different. Like here, see this. What I'm looking for? I am looking for same thing, return all of the song by an artist Elvis. So here I am specifying my table name is music, and I am creating a key condition expression which says artist should be for the value variable A, and variable A's value we have provided, or attribute value we have provided, is Elvis. So this is the way how I would query these NoSQL database. This is just one example. Some NoSQL databases would have a very specific way of querying the data, or some may support SQL also. Right. So focus here is on collection of document. This is a whole document returned to you, and then from there you would be able to filter whatever you require. So here the focus is on collection of the document, not on individual items within it. Right. Hopefully this thing is clear. When it comes to scaling, scaling is a method by which I am able to address or honor when lot of requests are coming to my databases. So in SQL databases, if you need more performance, you would do vertical scaling. You would keep on throwing more CPU and power to your database and keep on increasing in size, and that is how you would satisfy a number of queries which you can handle. Right. But you would soon hit a limit that how much economically you can put it into a box, because technically whatever the size of database is, it is still running on one single server most of the time. Yes, clustering happens, but let's consider that vertical scaling says if my server is not able to provide me capacity, I would replace it with a bigger server. I would replace with a bigger server. You would soon hit a limit that how much economically can be packed together into one server in terms of CPU and memory. So that's why we may hit some limit once we go beyond a specific point. That's why this, because we are using here a vertical scaling. Right? How tall you could build a building, right? So your Burj Khalifa, 150 plus floors. Can you make a building of 200 floors? Maybe. How many? Very less kind of a thing. So there will be some limitation which you may achieve once you start doing vertical scaling. But in terms of NoSQL databases, we utilize horizontal way of scaling. If you see this dotted line, consider we have created a cluster. And we may start with one node. If we need more capacity, second node, third node. If I need more, I could keep on adding more nodes into my system, and I should be able to horizontally scale my data need. Should not be a problem. So hopefully this thing is clear. This is a horizontal scaling and vertical scaling, right? Or you could go ahead and say this one, what you are seeing is a mechanism called scale up. I'm upgrading or getting up from what I had initially. And this one is referred as scale out. I'm scaling out. An opposite of that will be scale in. An opposite of scale up will be scale down. When I do not need, maybe I could bring it to smaller size. Instance should not be a problem. So hopefully this difference is also clear to you. The next difference is the way the transactions are processed into your database. What is a transaction? I don't want to go into the technical definition, but let's see that. Let's say I have a bank account here into, let's say, Barclays Bank. And from Barclays Bank, I am transferring transferring money to HSBC as a bank. Now, what would happen? I would have my account here. That is, let's say, A's account, and I want to transfer money into account of B. So this process of transferring data, where I would initiate something, that request will be processed by Barclay. Barclay and HSBC will be probably member of a common banking system. From that banking system, things will be processed. The data would be sent to HSBC. HSBC will perform its internal verification whether the account is active or not, whether it is a valid transaction or it is a fraudulent transaction, or maybe some other security check. And then the data would be, or the money would be transferred to the B. And then B could withdraw that money. Right. So what you are seeing here is a transaction. Now, in case there was some issue for HSBC and they could not receive it. So let's say if I send $100, either this person B will get $100 or it won't get $100. So it will be a binary way. Either it will be successful or it would be unsuccessful. It won't happen that out of 100 only $30 could be passed out and 70 returned to my account back. No, either it would go fully or it would be reverted back fully. That is what we mean by a transaction. So in SQL databases, we expect that transactions would be happening, and they use a very specific word to explain transaction that is called ACID support. So that is called atomicity, consistency, isolation, and durability. So that is a beauty of SQL database, that every transactions are happening either all or nothing. Only valid data is saved. If there is inconsistency, it won't be tolerated, it won't be saved. Transactions do not affect each other. So from my account, if I initiated one transaction of transferring $100 and another transaction was to receive $10, they are both treated separately, and you would have durability, which means return data won't be lost. This is what we refer as a ACID compliance. Now, this may not be very prominent now, because obviously SQL databases support it, but this support is also coming to NoSQL. Some NoSQL databases support this type of transaction too. So I won't say that it will always be true, because if I'm talking about Amazon based services like DynamoDB, in DynamoDB transaction support is there. You could follow transaction, but in technical term, this type of databases are referred as base compatible. Like acid and base in chemistry, kind of opposite. Same thing here. This is basically available. System does guarantee availability, which means your data would be available. Right, but it can be into soft state. It may change over time. Don't worry if you don't understand the soft state, we would talk about it. And your data may be eventually consistent. Maybe in a while everyone would have the same data available, but there may be a transitioning phase where some node may have the latest data and some node may still have old data. So that is the difference between SQL and NoSQL, or relational and non-relational database. We can go into more technical details of differentiation, but I think it is a good enough point to get started now. So hopefully this thing is clear. And in the next topic, we will discuss about the way AWS implement databases into cloud. So I hope you enjoyed, and I'll talk to you into the next section. Thank you.